Billions of years ago, life began on a young, hostile Earth. Simple organic compounds gradually formed more complex molecules capable of growth and reproduction, the earliest life forms. These primitive organisms were the ancestors of all life on Earth. At that time, Earth's surface was turbulent, with frequent volcanic eruptions, a toxic atmosphere, and no oxygen. Despite these harsh conditions, life found a way to emerge. To understand where life could have begun, we must first identify its basic requirements: water, a source of energy, essential chemical elements like carbon, hydrogen, nitrogen, and phosphorus, and a stable environment to support molecular assembly. Scientists believe life may have originated in deep-sea hydrothermal vents, tide pools, or even beneath the Earth's surface, places where these ingredients were available. These environments provided both protection and the necessary energy for chemical reactions to occur, laying the foundation for life as we know it. Since the earliest life on Earth emerged in a burrow without other living beings, it couldn't have been a heterotroph. It must have been an autotroph, relying either on sunlight or chemical energy from the environment. Many scientists believe that the first life forms likely derived energy from chemical gradients, especially in environments like deep-sea hydrothermal vents, where hot, mineral-rich water flows through the ocean floor, providing a rich energy source. Offer the essential ingredients and conditions necessary for life, the right chemical elements. When considering where life on Earth may have originated, scientists focus on locations that liquid solvent, water, and a reliable energy source. While environments on land or near the ocean's surface might seem like obvious candidates due to their access to sunlight, they also presented a major challenge in Earth's early days: intense ultraviolet, UV, radiation. Without an ozone layer to shield the surface, UV rays would have been lethal to fragile, newly forming life. As a result, early Earth's surface was likely too hostile for life to develop and survive for long. Triton TNG find a more promising cradle for life. Scientists turned their attention to a unique environment deep beneath the ocean's surface: hydrothermal vents. These vents meet several key criteria for life's origins and offer protection from the harsh conditions at the surface. Hydrothermal vents are found along the mid-ocean ridges, vast underwater mountain chains where tectonic plates spread apart and magma rises to form new crust. In these regions, seawater seeps down through cracks in the Earth's crust and comes into contact with magma chambers. As the water heats up, often exceeding 350 degrees C, 662 degrees, it dissolves minerals and reacts with the surrounding rock. This superheated, mineral-rich water is then expelled back into the ocean through vent openings, forming plumes that can be seen billowing from the seafloor. Although the environment around hydrothermal vents is pitch dark, it is far from lifeless. The vents support thriving ecosystems populated by organisms that rely not on sunlight but on chemosynthesis. These organisms use chemical reactions, particularly those involving hydrogen sulfide or methane, to generate energy. This ability to use chemical energy rather than sunlight is crucial because it means that life can exist and possibly even originate without relying on solar energy. Hydrothermal vents also offer something else critical: steep chemical gradients. A chemical gradient is a difference in the concentration of chemical substances between two areas. In the case of hydrothermal vents, the hot, mineral-laden water expelled from the Earth meets the cold, oxygenated seawater, creating sharp differences in temperature, acidity, and chemical composition. These gradients are ideal for driving the kinds of reactions that could lead to the formation of complex organic molecules. In modern biology, similar gradients are used by cells to generate energy through a process called chemiosmosis. This similarity has led some scientists to propose that early life forms used these naturally occurring gradients in hydrothermal vent environments of alarmus, long before the evolution of complex enzymes or energy-storing molecules like ATP. But what evidence supports the idea that hydrothermal vents might truly be the birthplace of life? One compelling clue comes from our understanding of the last universal common ancestor, or Luciae. Luciae is not the very first life form, but rather the most recent organism from which all modern life, bacteria, archaea, and eukaryotes descended. By comparing the genomes of organisms from all three major domains of life, researchers have been able to reconstruct some features of Lugo and infer what kind of environment it may have lived in. Surprisingly, many of Luciae's features suggest that it lived in conditions strikingly similar to those found at hydrothermal vents. Luciae likely thrived in an oxygen-free, high-temperature environment and relied on hydrogen gas and carbon dioxide for its energy and carbon sources. It also appears to have used metals like iron and nickel in its enzymes, metals that are abundant around hydrothermal vents. These characteristics strongly point toward a deep-sea vent origin, where the conditions match Luciae's needs far better than surface environments. In addition, many modern extremophiles microorganisms that live in extreme environments are found near hydrothermal vents. These organisms include thermophiles, which thrive in high temperatures, and methanogens, which produce methane, and they often possess ancient metabolic pathways similar to what scientists believe existed. Their existence today hints that such environments could have been cradles of early evolution. Of course, other hypotheses about the origin of life exist. Some scientists suggest that life could have begun in shallow tide pools where wet-dry cycles might have helped concentrate organic molecules. Others propose that life may have started in subsurface environments protected from surface radiation, or even that the essential building blocks arrived on Earth via meteorites from space. However, the hydrothermal vent hypothesis remains one of the most compelling and well-supported. The discovery of alkaline hydrothermal vents, such as those at the Lost City hydrothermal field in the Atlantic Ocean, has further strengthened this hypothesis. Unlike the more well-known black smoker vents that emit highly acidic and extremely hot water, alkaline vents release cooler, more pH-neutral fluids rich in hydrogen and other compounds useful for life. These vents form natural structures made of porous minerals which may have acted as protocells, providing compartments where early chemical reactions could occur in isolation from the surrounding ocean. These mineral pores might have also helped concentrate organic molecules and protect them from dilution, a key challenge in ocean-based origins to reach area. In summary, hydrothermal vents deep beneath the ocean's surface offer a compelling setting for the origin of life on Earth. They provide the necessary ingredients: water, essential chemical elements, and a powerful energy source in the form of chemical gradients within a stable and protective environment. While the mystery of life's origins has not yet been definitively solved, the study of these deep-sea environments continues to yield important insights into how life might have begun, not only on Earth but possibly on other ocean worlds in our solar system, like Jupiter's moon Europa or Saturn's moon Enceladus. Despite our deepening understanding of life's history, we still don't know exactly what the last universal common ancestor Luca is not a fossil we've dug out of ancient rock, nor is it a living species preserved in some remote corner of the world. Instead, Lugo is a theoretical construct pieced together from the genetic traces it left behind in its descendants. Every living organism on Earth today, whether it's a bacterium, a mushroom, or a human, shares some core genetic features. These common genes are found across the three domains of life: bacteria, archaea, and eukarya. Because they're so widely shared, scientists believe these genes were inherited from a single ancestral organism, Lugia. By analyzing these universal genes, scientists have made educated guesses about the kind of environment Lucia lived in and the traits it possessed. For example, Lucia's genes indicate that it lived in a hot, oxygen-free, anaerobic environment and relied on chemical gradients to produce energy, just like many microorganisms that live near hydrothermal vents today. This connection has led scientists to consider hydrothermal vents as likely locations where Lucia and possibly life itself first emerged. Hydrothermal vents are cracks in the Earth's crust, typically located along mid-ocean ridges, where seawater seeps down into the crust, becomes superheated by underlying magma, and is then expelled back into the ocean. These vents create highly dynamic chemical environments rich in minerals and steep gradients in temperature and chemical concentration. These gradients are thought to have played a crucial role in allowing early life to harness energy from metabolism before the development of more complex cellular machinery. There are two major types of hydrothermal vents: black smokers and white smokers. Both are rich in chemical compounds, but they differ significantly in their temperature, acidity, and chemical makeup. Black smokers are named for the dark, smoky appearance of the mineral-laden water they release. These vents emit superheated water, often exceeding 350 degrees, that is highly acidic and packed with metals such as iron, copper, and sulfur. This mineral-rich environment supports unique ecosystems, including tube worms and extremophile bacteria. However, most scientists now believe that black smokers were likely too hot for Luca. While modern extremophiles can survive near these vents, Luca probably lacked the complex adaptations needed to withstand such extreme heat. Proteins and other organic molecules essential for life would likely have broken down in those conditions. That's why attention has shifted to the second type of vent: white smokers. These vents emit cooler, alkaline fluids, usually under 100 degrees C, and are less acidic than black smokers. Instead of dark, mineral-laden plumes, white smokers release lighter-colored fluids rich in compounds such as hydrogen and methane. While these vents also contain essential minerals, their relatively moderate conditions make them a more plausible setting for the early development of life. Among white smoker fields, one location in particular stands out as a prime candidate for the cradle of life: Lost City. Located on the mid-Atlantic ridge, the Lost City hydrothermal field is a system of towering chimney-like formations made of calcium carbonate. These vents release fluids with a pH of 9 to 11, extremely alkaline at temperatures ranging from 40 to 90 degrees. Though this may still seem hot, it's far more hospitable than the conditions around black smokers. Lost City vents are also rich in hydrogen and methane, both of which could have served as fuel for early metabolic reactions. These gases offer a crucial energy source in the absence of sunlight, supporting the theory that the first life forms were autotrophs that generated energy from chemical reactions rather than photosynthesis. However, one critical ingredient for life, carbon dioxide, is notably scarce at Lost City. Carbon dioxide is a key carbon source for many biological processes, including the synthesis of organic molecules. So where did the carbon dioxide necessary for life come from? Scientists propose an intriguing solution. Adjacent black smoker vents may have supplied the missing carbon dioxide. Though black smokers were too extreme for Lucier to live near directly, their expelled CO2 could have diffused into nearby regions, including the more moderate environment of Lost City. In this way, Lost City might have benefited from the best of both vent systems, the hospitable conditions and energy-rich compounds of white smokers, combined with the carbon input from nearby black smokers. The structure of Lost City also offers another important advantage. Its porous, rocky chimneys formed by the precipitation of calcium carbonate contain numerous microscopic chambers and pores. These natural compartments could have served as primitive cells where organic molecules were trapped and concentrated. Within these small spaces, chemical reactions could occur more easily, possibly leading to the formation of more complex molecules like proteins, lipids, and a nucleic of prose. These mineral compartments might also have helped create and maintain chemical gradients similar to those used in modern cellular respiration, providing a bridge between geological processes and biological metabolism. This setting aligns well with what we've inferred about Lucier's biochemistry. Lugoe appears to have used iron, sulfur, proteins, and other metal-based catalysts common in vent environments for its metabolic reactions. It also seems to have relied on the energy stored in protein gradients across membranes, a trait shared by nearly all life forms today. The mineral structures at Lost City could have played a key role in helping these early systems emerge. Though Algae itself was not the first life form, it represents the last ancestor shared by all current life on Earth. That means life may have existed before Lucier, but those earlier forms either went extinct or evolved beyond recognition. Luce's descendants, however, radiated out into all the biological diversity we see today, from single-celled bacteria to complex multicellular organisms, including humans. In conclusion, the Lost City hydrothermal vent field provides a compelling and well-supported environment for the origin of Focroft. Its moderate temperatures, alkaline conditions, rich supply of methane and hydrogen, and natural porous structures make it a likely cradle for the emergency nearly metabolism and replication. The proximity of black smokers may have added the carbon dioxide necessary for more advanced biochemical processes. While many questions about life's origins remain unanswered, the discoveries at Lost City bring us closer to understanding how life could have emerged from the geochemical processes of a young Earth, and perhaps how it might emerge elsewhere in the universe.